So the expectation is equal to 0, meaning that the process does not depend on time, obviously. I mean, the expectation doesn't depend on time. Okay. Now, for the variance, okay, we get a different story basically. So the variance of the process is going to be equal to, I mean, you have, this is going to be the expectation of the squares, all right, minus the square of the expectations, and of course the expectations of the process are equal to 0, as you see. So this is just going to be equal to the expectation of the squares, okay, because that's obviously 0. And so here you have basically the expectation of yt squared, right? And that's what you would get, okay? And we have seen that this is equal to the expectation of sigma squared, okay? So basically, because this is a stochastic volatility type process, okay? Again, so, you know, I mean, we have seen this here in the noise. You don't need to prove this again anymore, okay? Now we take the expectation of sigma squared. Now, what is the expectation of sigma squared again? So what we have is basically the expectation of the sum is equal to the sum of the expectations. That's going to be the first statement, okay? And the second statement is that the linear transformation of an expectation is going to be equal to the, the expectation of a linear transformation of the process is going to be equal to the linear transformation of the expectation of the process. So this means, I mean, basically, according to the previous equation that you've seen, this is going to be, I mean, okay, let me just do this one step here. So this is going to be the expectation of the following expression. So you have the alphas, okay? So here you have yt minus 1 squared plus blah, 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 blah. So here you have plus alpha q times yt minus q squared, okay? So and then plus beta 1 times sigma t minus 1 squared plus sigma beta 2 times sigma squared, sigma t minus 2 squared, and then plus beta q times sigma t minus p squared. Okay? Good. Now, of course, again, the expectation of the sum is the sum of the expectations, and the expectation of the linear transformation is going to be equal to the linear transformation of the expectation. So here you have alpha 0 plus alpha 1 times the expectation of yt minus 1 squared, right? Then plus the y alpha 2 blah 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 plus etc. etc. So then you have alpha q times the expectation of yt minus q squared, all right? And then the second part is going to be beta 1 times the expectation of sigma squared t minus 1 plus beta 2 times the expectation of sigma 2, sigma t minus 2 squared, and so forth. So then you have beta q times the expectation. So beta p, so not q. I missed this part, sorry. Here you have beta p, not q. The leg order can be different. Sorry, guys. Okay, so here you have p, of course, in the general case. So beta p, not q, okay, times the expectation of sigma t minus p squared. So this is sigma t minus p squared. There you go. This is going to be again.
So here, y is following a GARCH model, a GARCH distribution or ARCH distribution?
Oh, okay, yeah. I see. So I mean, this is a special case, right? You can omit this because I was sleeping. That's why I was looking at the second part of the exercise. So not the. I mean, you can. Okay, maybe you do the following. Okay, so we generalize this. Okay, so then basically, okay, you would. I mean, okay, what would you do? All right, so now let's keep this. So then basically, the second part of the exercise is covered. And if you have a GARCH, if you have an arch quotient, it's just the sum of these coefficients has to be less than or equal to 0, because the betas are going to be equal to 0. So that's just a special case. Okay, all right. I just wanted to focus on the arch process, but I forgot to do this. I don't know why. Anyway, so guys, I mean, this is, you've seen this here. This is the expectation of sigma squared, right? And you could say that since this is equal to the variance of the process, okay, this is equal to the variance here of the process, and that is also equal to the variance of the process. The variance should not be time dependent, okay? So the variance should not be time dependent again, so this is basically equal to the variance of the process at point t minus 1, and this is equal to the variance of the process at point t minus p, obviously, okay? And so this is equal to the variance of the process at t minus 1 as well, okay? Alright, so in this part is going to be equal to the variance of the process at point t minus q, obviously. So these are all variances, because this is the property of the size of the process. Now, if you want to make sure that the variance does not depend on time, okay, so if the process is stationary, then the variance would not depend on time. So the variances are going to be equal, okay? So all variances would be equal, okay? So I'm talking about this one, this one, this one, this one, and this one. These expressions would be all equal if the process is stationary, because the variance does not depend on time if the process is stationary. You understand? So these things are equal, right? So I'm just calling them, okay, so I call them just the variance of the process, okay? So the variance of the process here, okay, so since y is stationary, this implies, okay, that the variance, okay, so I'm using this expression, so the variance of the process, okay, is equal to alpha 0 plus alpha 1 times the variance of the process, okay? All right, plus blah, 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 plus alpha q times the variance of the process, okay? And then plus beta 1 times the variance of the process. So these expressions are all the same. Again, because the variance should not depend on time. Okay? All right? Otherwise, the process would not be stationary. Okay? Right? So if that was not the case, then the process would not be stationary. All you need to do now is to solve for the variance. Okay? So basically you would do is you would factorize, okay? And then you would take the, this is super easy right now, I think. Okay, so here on the right hand side of the equation you would factorize. Okay, so if you did this, and then you would factorize here on the left hand side as well. So to get rid of these expressions, so then the variance of the process, okay, so I skipped this because this is elementary, okay? So in that case, the variance of the process will be equal to, and this is what you're going to get, so this is going to be equal to alpha 0 divided by, and then you have 1 minus the total sum of the alphas, okay? So the total sum of the alphas, all right, and then minus the total sum of the betas. Obviously, okay? That is elementary. Okay? So, now, of course, this coefficient here, guys, is greater than 0. Right? By definition. You know. So, and that means that the denominator cannot be negative. Okay? So the denominator cannot be negative. So this implies, on the other hand, that the denominator here, so 1 minus the whole thing, okay? This is the whole thing here, is also greater than 0 as well. Okay? Because if that was not greater than 0, the variance would be negative, which is not possible by definition. Okay? Now, if that is basically greater than 0, by rearranging that expression, you would get, I mean, basically, if you solve this inequality, right? So you would get that, okay, 1, okay, or let's say the sum, you should put these sums to the right-hand side of the inequality. So you have 1 is greater than the total sum of these coefficients. And if 1 is greater than the total sum of the coefficients, that means that the total sum of the coefficients is less than 1. Okay? So the total sum of these coefficients, all right, is going to be less than 1. All right? Okay? So again, I mean, if basically the process follows an arch type process, then the betas are 0. So then this includes basically the case where you would, you know, you would have for the arch process that the stationary condition, that basically a necessary condition is that the total sum of the coefficients is less than 1. 1, sorry, not 0, 1, yes. I meant to do this. Okay? So if 1 is greater than the total sum, then of course the total sum is less than 1, obviously. Okay? So that includes the case where basically you would have a stationary arch process. Okay? Now maybe we can consider 6.3. Okay? So that was, you know, the rearrangement. Okay? So 6.3 is about, as I said before, this is rearranging the GARCH process. So basically the statement is, okay, so exercise 6.3 is about showing that if that's basically, if Y is or can be written as a GARCH 1-1 type process, okay, then this should imply that basically sigma squared shall be or can be written as alpha 0 divided by 1 minus beta 1 plus alpha 1 times, and you have this kind of weird sum here, so the sum starts at j is equal to 1, and you have beta 1 to the power of j minus 1 times y t minus j squared. Okay, so j is basically the summation index that you would have here. So what you basically would do here is that the GARCH 1-1 type process indicates a autoregressive process of order infinity of the squares. Now, of course, the coefficients are predetermined here, right? So the coefficients beta 1. Okay, so I mean, the regression coefficients only depend on beta 1, of course, right? So in a more general case, you would have different coefficients as well. But this is just another representation of the process, and the question is, why is that? So we'll talk about this now, okay? So how would we do this, okay? Now, first off, you would, okay, so what you would do is, okay, so you would consider, for instance, how the process will look like. So the process looks like this. So you have alpha 0 plus alpha 1 times yt minus 1, okay, plus beta 1 times sigma t minus 1 squared. Okay, so again, this is how the process is. Okay, so sigma squared basically, depending, I mean, this is the basic definition of the GARCH 1-1 process, okay? And what you would do is you would replace basically this expression here, okay? So what I'm doing is I'm replacing this expression here. By what? Okay, let me just emphasize here what I'm replacing it with. So here you have, of course, if sigma squared t is equal to this expression, then sigma squared t minus 1 is going to be equal to, analogously, so here you have alpha 0 plus alpha 1 times yt minus 2 squared plus beta 1 times sigma t minus 2 squared, obviously. Okay? So I'm using these colors because you see that what I'm replacing that with. So what I'm doing is I'm putting this expression here into that. Okay, so and finally I get the following result. Okay, so you would have basically you have alpha 0 plus alpha 1 times yt minus 1 squared. Okay, and then beta 1 times the whole thing. Okay, all right. So beta 1 times the whole thing would be beta 1 times alpha 0, right, plus beta 1 times alpha 1 times yt minus 2 squared, and then you have beta 1 squared times sigma t minus 2 squared. Okay? So I'm multiplying each and every expression here from it by beta 1. Okay? Okay? Good. Now, what I'm doing now next is I'm going to replace in this expression similarly. Okay, so that expression will be replaced as well. Okay, so let's see what will happen. But first off, I will rearrange it a little bit so I recognize some systematics here. Okay, so what I'm going to get here is that basically you have alpha 0. Okay, so alpha 0 is here. This one and this one. So this is going to be equal to 1 plus beta 1. Okay, so I'm factorizing it here. And then you're going to get, okay, so what I had here is considered as this one and this one. Okay? So alpha 0 times 1 is the first one, and alpha 0 times beta 1 is the second one. Okay? Obviously. Okay? So then you would have, you know, these kind of expressions here. So alpha 1 times that expression plus beta 1 times alpha 1 times that expression. So I'm putting at the alpha ones first, okay? So you have alpha 1 times yt minus 1 squared, and then you have alpha 1 times beta 1 times yt minus 2 squared, okay? And then you have the remaining one, okay? Again, so beta 1 squared times you have sigma t minus 2 squared. Now what I'm going to do here is I'm going to replacing sigma t minus 2 squared again. So what you've seen is by means of the following expression. Okay, so of course depending on, you know, the basic definition, if sigma squared is equal to that expression, then sigma squared at t minus 2 is going to be equal to the following. Okay, so let me just illustrate what I'm going to replace that with. So sigma t minus 2 squared is going to be equal to alpha 0 plus alpha 1 times yt minus 3 squared, right? Plus you have beta 1 times sigma t minus 3 squared. Okay. Alright, so what I'm going to do here is I'm going to put this expression here into that. So, and then you see what, you know, what will be next. So here you have beta 1 squared. So the next thing will be alpha 0 times 1 plus beta 1 plus beta 1 squared, right? Okay? And then you will see the rest. Okay? So then you're going to have, okay, so alpha 1 times yt minus 1 squared, okay? Then you have plus alpha 1 times beta 1 times yt minus 2 squared, okay? And finally, you'll, I mean, here in regarding these expressions, so you will have, and this is what you have here, beta 1 squared. So you have alpha 1 times beta 1 squared times yt minus 3 squared, okay? So that's the mechanism that applies here. And the final one will be equal to, so beta, this is what you will have, okay? So you're going to replace this. So beta 1 squared times beta 1 times sigma squared at point t minus 3. It's going to be equal to beta 1 cubed times sigma t minus 3 squared, okay? So that's, you know, the mechanism that applies here. And now suppose that you do this infinitely many times, okay? So if you do this infinitely many times, okay, so after basically the nth iteration, okay, you would get, you know, the formula that basically we would consider, okay? So I'm going to finish here and then we'll finish, we'll stop here and then we'll finish it next time. So, but maybe you can try this. All you need to do is just to apply the geometric series, okay? And as you would see, this expression here, this expression, okay, so here you have, after n iterations, okay, you will have that this expression will converge to 0, okay? So this one, okay? I will stop here, so if you repeat this, if after 2 iterations you have beta 1 squared, if you do this another one, then you do the final one with beta 1 cubed, etc., okay, so that's how basically the process evolves, okay? And then you would generalize that, and then of course you would figure out that this expression will converge to 0, right? So then this will be dismissed, so the only expressions that will remain are going to be here, okay? But due to the matter of time, I think I will stop here and then we'll finish there next time. Yes?
What's about the alpha on the last?
These will remain. Okay? So you have alpha 1 times the whole thing. You can see this here.
Yeah.
So you have alpha 1 times the sum, blah blah blah, right? And you do this infinitely many times. If you do this infinitely many times, then basically here you would get the geometric series. This is the geometric series of the first part, okay? So this corresponds to the first part, okay? So this one, according to the geometric series. And this part, okay, corresponds to the sum, okay? All right? And that one will be dismissed after infinitely many iterations, because the expression beta 1 to the power of 3 will converge to 0. Okay? Okay guys, now we'll stop here and then we'll finish next time. Okay? Alright. Next time I would like to talk to you about the topic, so we'll finish this exercise. So maybe you should look into the studies that I gave you or the books that I gave you, and maybe pre-select 1 or 2 studies that you might be interested in. Okay, so I'm not saying that you should select something for as a mandatory thing, but maybe you should look into the literature and see what kind of stories you would be able to replicate. Okay, of course in a small version. Okay, so you don't need to repeat this as a whole, right? So maybe just part of it, like let's say, okay, so 4 to 5 pages max. Okay, that would be just it. Okay, but you should have 1 or 2 tests that you would examine. Okay, all right. So please, this is how I would do. Okay, so I finished the exercise. Then I would like to talk about your person, each and every one of you. Okay, all right. So we do this maybe next week, and then let me just announce this so we can make appointments, so you don't need to come at, let's say, 8:30, okay, and talk about it. So so what you would basically do is maybe you can send me an email, okay, and we'll arrange something, okay, so you don't need to come on both occasions, let's say. Okay, all right. Good. Okay, guys. Okay, so check your emails. I will make some announcements now. Okay. All right. Thanks.